record, right? Am I recording? Am I recording? Am I recording? Record me. What? What? Why? Which? I am recording. Okay. Okay, so on your paper, you can't do this in the Google form, whatever. On your paper, sketch out what does sine of x look like? Real fast. On your paper in front of you. Also, what does cos of x look like? Be as specific as you can without, using a ruler or a calculator. Do it from your head. I want you to see what's in your head. Sine and cos, graph them. Sine of x, cos of x. Sinks, cosecks. You know what? Let's. And here we go. Here's sine. Oh, that's a crappy sign. My sign is no. I want this to look pretty, just like me. No! Whatever. And of course, they repeat before and after, but I'm going to focus on just the 0 to, what is the domain? Well, the domain is all round numbers. How far does it take to repeat one cycle? 2 pi, not 360. Take your degrees, and you should be able to convert degrees to radians. I might ask you for degrees or give you degrees here, but all internal calculations thou shalt do in radians. Set thine calculator to radians. That might be worth remembering, by the way. How many degrees is equal to 1 radian? How many radians is one cycle? Cycle. Write it down on your paper. Test yourself real fast. Test yourself before you arrest yourself. Cos and sine repeat after 2 pi radians. 2 pi is a full cycle. Oh, that's actually not that bad. 2 pi radians equals 1 cycle. Well, if we set up the equivalence, 2 pi radians equals 1 cycle equals 360 degrees, you can solve. Divide both sides by 2 pi, and you get roughly 57.3 degrees is 1 radian. Do you see how I did that? 2 pi rads, 180 degrees, divide by 2 pi, and you get 1 rad equals 57.3 degrees. 180 over pi. Great. Some things to know. Hey, how tall does sine get? How tall does cos get? This, I hope you will believe me that they go up as high as 1 and they go down to as low as, big shocker, -1. Yeah? Deja vu, how do you feel about this level of trig? We're not doing no trig identities, but you do, and I'm not going to demand that you remember any trig identities, I don't think, ever at all. But I am going to ask that you know which one is sine and which one is cosine, how big and how small, and how long it takes to repeat. How long along the horizontal axis does it take to repeat? Is good? Feel okay with this? Question me. Radians. 1 full cycle. Of a sine or of a cosine. You have gone through 1 complete oscillation. You have returned to your original phase, whether you started at 1 or whether you started at 0 and going up. Great. Okay, so I'm going to define, previously I talked about peak voltage and peak current as the height of the sine wave. I would like to be able to talk about sines and cosines. By the way, very first thing, sorry, let's do this in order. Very first thing is, when I say sinusoidal, I am not just talking about the sine function. When I say sinusoidal, sine and cosine are both sinusoidal waves to me. I do not use the word cosinusoidal. Sine wave for me is anything that wiggles like this. When it is important, I will distinguish between, oh, hey, we started at the origin, sine. Oh, hey, we started at the max extension, cosine. Sometimes I will care about sine versus cosine. In general, I see a wiggle. I see a wiggle with this behavior that looks like sines and cosines. I will just call it sinusoidal. The height of the sinusoid function I have previously identified as the peak amplitude, the peak intensity, the peak current, and the peak voltage. Now I'm going to have a more generic word for it. I'm simply going to call it the amplitude. Amplitude could be anything. Amplitude is the height of the sine in whatever you're graphing. We're going to be talking about things which are moving back and forth. And then the amplitude will be a measure of distance, the distance from the equilibrium position. We can also still talk about a sinusoidal voltage. You'll apply a sinusoidal voltage in lab to the wave drivers to make sine waves along a string or whatever. Then the amplitude will refer to the maximum voltage that is given. In any case, you look at the vertical axis, say, what is this graphing? And you could talk about the amplitude of anything. The amplitude is the maximum with respect to center line, with respect to equilibrium, the maximum value of the vertical axis. The horizontal axis, also watch both axes. Message to the wise here. Both axes are important. The horizontal axis we're going to be talking about this week is time. A oscillation, a vibration is a wiggle at one place as time passes. Next week, we're going to start talking about waves. Waves are oscillations that spread out through multiple locations. So next week, we're going to graph sine waves, where the vertical axis is some displacement, and the horizontal axis is, well, there will be two kinds. We'll have a horizontal axis of time, like this week, and we'll have another graph where the horizontal axis is position. You're going to have to watch out for this carefully. So, the moral of my story is to interpret carefully, my friends. The horizontal axis is time. Then we could talk about from a peak amplitude to a peak amplitude, the horizontal time difference that defines period. That is not a universal thing. Next week, we will have a sine or cosine wave, and we will identify the horizontal distance on the graph as something called wavelength. So watch out for it and interpret. When we're talking about an amplitude in any way, shape, or form, displacement in this case, amplitude versus time graph, this measurement is getting the time to repeat. That is the definition of one period, as we did before. Anyone remember what the reciprocal of period is? Frequency. What's frequency measured in? Hertz. By the way, what do we measure period in? Seconds. It's a time, so seconds. Good. Okay. Now, we've talked about sine waves. There is a mathematical relationship between the motion, and when I say motion, I don't just mean velocity, the position, the velocity, the acceleration, the kinematics, where and how fast something is, and the forces exerted on it. What we did last semester all the time was we talked about things that had simple acceleration. That is to say, uniform accelerations. We might have an acceleration that started off 0 and then became, 3, and then maybe later became -5 meters per second squared. But we never had an acceleration. We never had forces that varied in more than piecewise constant form. Now we're going to change that. Sinusoidal motion, all simple harmonic motion, results from when you have a force function that varies with where you are. That is to say, linear restoring net force is what is always associated with simple harmonic motion. Simple harmonic motion, sinusoids. Sinusoidal motion, vibration, oscillation. Let's look at these words, by the way. Linear, restoring, net. What's linear mean? Right? Not constant, linear. A graph of what versus what is linear? A graph of force is linear. Force versus what? Force versus position. I did not say that. I should have said a linear position restoring net force. Okay, so hey, pay attention. This is not on the slide. The graph of force versus where you are must be a diagonal line. Diagonal line. Diagonal. In particular, diagonal with negative slope. Couldn't think of it. Because you need to be experiencing a force in the restoring direction. Restoring means the force needs to be negative when you're on the positive side of the force needs to be negative when you're on the positive side of the equilibrium point and positive when you're on the negative side of the equilibrium point. Positive versus negative position, positive versus negative force. That means that if you extend a spring, which direction does the spring pull you back? If I push the spring this way, it pulls me back that way. If I compress a spring shorter than its equilibrium, it tries to extend me back in the returning direction. That's what I mean by restoring. The force must be in the opposite direction as the position with respect to equilibrium. Force pushes backwards, back towards. You can have a linear force. For instance, if I have something balanced on top of a triangular wedge, if I have a ball on top of a triangular wedge, there is zero force when I am sitting exactly at the peak. And then, actually it wouldn't be a triangle, I guess it would be a round shape, whatever. And if I go on the right side of the wedge, I can have a linear force, which gets stronger and stronger the further right I go. If I'm on the left side of the wedge, I can have a linear force, which gets stronger and stronger the further left I go. But those are not restoring forces. If I have a box on top of a rock, on top of a hill, top of a mountain, and the box gets bumped from its equilibrium position, will it return to the peak of the mountain? Of course not. On the other hand, if I've got a box bobbing up and down, a particle bobbing up and down from a spring scale bobs up and down around its equilibrium, because when the spring is longer, the spring tries to make itself shorter. When the spring is shorter, gravity tries to pull it longer again. Yes? So, linear must be a straight line in position versus force graph. Restoring the direction of the force must try to push you back towards equilibrium. Net force, very important, very important. Just because if you have a spring does not mean that your F equals ma is kx. Remember what I banged into your brains over the course of like 2 months last semester? Must be a total force, must be a linear restoring force. Just because you have a spring does not mean you always have oscillations. The total force, spring and all other things, must be linear. Okay, so what? If force is linear, restoring, that is to say in the returning direction, then your kinematics, your position, your velocity, and acceleration will all be sine waves. I should be a little more precise on that. Position, velocity, and acceleration will be sinusoidal. If position is sine, it actually will discover in a little bit that velocity will actually be a cosine wave, and an acceleration wave would be a negative sine wave. We'll get there. If position is sine, velocity cannot also be the same sine function. We'll get there. Okay, Google form, what are we at? A, we haven't done any. Google form A, what did I just say is the motion, the kind of the mathematical form of the equation that describes the motion itself? Read carefully. Okay, that's question A. Question B is the type of function that describes the force to get SHM is. What kind of force results in SHM? Quadratic, exponential, inverse, linear, sinusoidal. Okay, so question A is, what does the motion itself look like in simple harmonic motion? Question B is, what is the force formula that makes you have simple harmonic motion? And the correct answers are sinusoidal and linear, respectively. From the previous slide, your motion will be sine waves, cosine waves, whatever. Your motion will be wiggles if your force is linear in position. Incidentally, anyone with solid calculus, see me in office hours and I will prove that to you. It does take calculus, but it's not even super advanced. Whoopsie. I thought I had cleared my previous drawings. Okay, well, here we go. Merry Christmas. I give you a formula. Simple harmonic motion, the x versus t can be described using the function a cos omega t. This is any kind of motion. We will use this same formula to talk about mass on a spring, cork bobbing up and down on the ocean, mass on a spring horizontally. What else? We could talk about voltages as amplitude cos omega t. We can talk about pendulums, children on a swing swinging back and forth as a cos omega t. Or a sine omega t. Remember, I am not stuck with using cos or sine. I'm going to give this example of cosine in these lectures. But what happens if I have something that starts at the origin and then wiggles away from the origin? What function would you use? Use the function that makes sense for the problem. That would be x equals a sine omega t. How do you know which one to use? Well, you consider, do I start at the origin? Do I start at the max? Use which one makes sense. A is the amplitude. Why does it make sense to say A times cosine? How big can cos get? The biggest extent that cos can get is 1. If I multiply something that can get only as big as 1 by A, then does it not logically follow that A tells the maximum height of the function? Of course, that's where the amplitude belongs. Maybe it's a little more mysterious why I do cos of omega times t. First, tell me this. Riddle me this, Batman. Riddle me this. How long in time does it take to go how much time does it take to go through one full cycle? No. The inside to cosine must be 2 pi. The inside to cosine must be 2 pi to go through a full cycle. How long must t go through? Trick question, I don't know. T must go to 1 period. So when omega times t equals 2 pi, then 1 full cycle. Okay. Well, when we have gone through 1 full oscillation, I no longer refer to t as lowercase t. What symbol do I use to refer to it as 1 full time? Period. Frequency is the reciprocal of this. When t has gone through a full cycle, I promote the independent variable t to its capital form. And what do I call it? What do I call capital T is period. Period is that special time, the time it takes for lowercase t to cause 1 full oscillation. Okay, can anyone solve for period for me? What is period? Take the frequency. Take the equation and solve for capital T. What do I get? Or for that matter, wait, hold on a second. What's the relationship between period and frequency again? Reciprocals? Could I take the reciprocal of both sides? Oh my sweet baby Lucifer, will you look at that? F equals omega divided by 2 pi. Last semester, I could have sworn there was a relationship between two variables. Maybe if I solve for omega. Does that tickle any neurons here? Whoopsie. Does that trigger any traumatic memories? Angular frequency, baby! 2 pi tells the number of radians per cycle. F tells the number of cycles per second. Rads per psych, psychs per second, rads per second. Omega is angular frequency. Except if we're not talking about angles, if we're not talking about rotations themselves, I am going to not refer to this as angular frequency. The other name that is more common in this context is natural frequency. If I am talking about angles, you could still call it angular frequency. At any rate, the relationship is the same as we encountered last semester. 2 pi f is angular frequency, natural frequency. Radians per second. I want to emphasize the units for A amplitude are whatever you're measuring the oscillations of. We'll often talk about amplitudes of position. So we'll talk about this in meters. Omega in natural frequency is radians per second. Distinguish carefully omega, radians per second, frequency, F, cycles per second, or hertz. Omega and F are different but related variables. Omega is natural. F is no adjective. Both are kinds of frequency. So if I just say frequency, which one am I talking about? F. If I say natural frequency, which am I talking about? Omega. If you don't see the word natural or angular, I'm not talking about omega. If you don't see the word natural or angular or whatever, I'm talking about ordinary frequency. Okay? If you see F, what are the units? If you see the units radians per second, which one am I talking about? Yes. Yes? Watch out for these. If you mix up which one I'm talking about, you can't possibly get it right. Can't possibly solve any given problem. They're intimately related. They're just off by a factor of 6.28. If it uses the Greek letter omega, if it has the word angular or natural in front of it, if the units are radians per second, that's 1. If it doesn't have the adjective in front of the word frequency, if it uses the letter F, or if it uses the units hertz or cycles per second, that's the other. Okay. Yes. Yes. I want to put this connection in here, even though in the context that I'm talking about, I will almost always refer to this as natural frequency. In my mind, natural and angular are so synonymous, you may catch me saying angular frequency from time to time. Here's a summary of what we've just said. Frequency F in hertz, period T in seconds, angular / natural frequency omega in radians per second, and the relationships between these three. I strongly encourage you, don't memorize all of this. Memorize the definitions and know a path from one to the other. For instance, if you know that frequency and period are reciprocals, do you really need both formulas? As long as you know how to take the reciprocal of a fraction, you don't need to memorize both of these. Personally, what I do is I know that omega equals 2 pi times frequency. Omega equals 2 pi f, and I can manipulate from there. But there you go. There are the relationships that you need to be able to write. Solve your homework and lecture slide and quiz and exam problem. Capiche? I've got some definitions. I've hopefully motivated why omega pops up, but there should be no depth here. This is like an inch deep, 4 terms wide and 0 inches deep. Ready for the next? Great. Okay, whoopsie. Well, now you've seen it. Screw it. We're coming back to it. We're coming back to it. We'll go on and come back to it. I select what? Select all, clear pages, done. Okay, let's try this again. Hey, would you remind me to come back to this at the end of the lecture? I wanted to practice with this, but not having just seen it. Okay, let's talk about a particular example. Well, there are 2 examples, 2 scenarios, 2 systems that I'm going to ask you to solve problems with. The spring oscillator and the pendulum. The pendulum's a little more complicated. We'll deal with him in detail tomorrow. So let's talk about the spring oscillator and get a foundation for this today. Here's a spring oscillator. You take a box, you put them on a spring, that's it. No friction. And it doesn't matter if it's vertical or horizontal. You can have a spring going horizontally along a frictionless level surface. You can have a spring bobbing vertically just under gravity. Same E equals same E. The motion is the same. The equation, the core relationship is the same. It's got to be frictionless. If you introduce friction, if you introduce drag, if you introduce a motor which is driving the other end of the spring back and forth, the equations get god-awfully complex. 3rd year physics major complex. You don't want to go there. Maybe you do. We're not going there. What I will describe most often for the sake of simplicity is a box of mass M rests on a horizontal frictionless surface attached to a wall with a spring of spring constant K. K, what's K? K, spring constant, stiffness, Hooke's law constant K. Let's do a problem with him for a second to refresh your memory on what K must mean. The core formula, K does not stand for core. The core formula is F equals negative Kx. F is the force exerted by the spring. K is this spring stiffness constant. And X is the displacement from equilibrium. Not the length of the spring, the change in length relative to equilibrium position. Okay, do you remember that, negative Kx? Does that sound familiar at all? Write it down if you don't remember him at all. F equals negative Kx is the spring law. Okay, now I'm going to give you a problem. I just said that all of my boxes are going to be horizontal for the simplest case. Now I'm going to give you, we're not going to talk about the oscillations of this system. Let's just take a second and let's talk about the spring itself. So I'm going to give you a vertical problem here, but we're just going to talk about the strength of the spring itself. If I have a box dangling 5.6 centimeters below its equilibrium position, 1 kilogram mass dangling from this spring will be in balance there. If I take off the 1 kilo mass and replace it with a 1.3 kilo mass, how stretched is that spring? No oscillations, no vibrations, just an equilibrium balance here. Can you use the equations? I'm going to stop talking. Question C, are we at? Google Forms C. See if you can wrestle through this. If anyone has to ask what G is, hint, hint, hint. Work with your neighbor, though. Okay. Oh, you should talk to each other. Help each other out. It's good for you. Your brain hurts. Does it frequently hurt? Oh, sorry. Give me units, please. Don't just say 5, say 5 what? Also don't say 5 because that's wrong. Okay, 1 minute. As we say in Spanish. Sí. All right. So, not oscillations, just straight balance of forces here. What forces act on the box? Well, I'd say if it's dangling from a spring force. If I didn't care about the stretch, I'd call it a tension. And wait, mg. Okay, so if I take this, I could do this in 2 steps. I would suggest the first step is solve for k. K does not depend on the stretch of the spring. So I'm going to get a constant here. mg over x is the spring stiffness. mg 1.0, 9.8, 0.056 equals 175 newtons per meter. That's K. Is that the answer? No, I didn't ask for K. I asked for the stretch of the spring. However, having found K, I could then calculate any given stretch. If I use the formula again, mg equals kx, and I plug in m is now 1.3, I get 7.3 centimeters. Yeah. So I always encourage you to reason about directions separately and magnitude separately. So here's what I'm imagining. If the spring is stretched by a weight hanging from it, the direction of the force is up. And that's balancing the direction of the weight force, which is down. So I have written down mg equals kx to say that the magnitudes of those 2 forces are balanced. If you want to do this all in one master mathematical equation, you're going to have to consider, is x positive or is x negative? Is the spring below or is the spring above the mass that is being bobbed on? Or is it horizontal? Which direction is the force in? Which direction is the origin length of the spring? Ooh, that gets complicated. There is a way to do it logically consistently, but it's complicateder. What I'm going to give you is something where you can reason about this magnitude and this magnitude are equal. Yes. So I would say no, don't tangle with the negative there. Good question though. Other questions? Okay. D, when I displace an object from its equilibrium and the force pushes it towards what? And the force which pushes it back towards equilibrium is what? The resulting motion is simple harmonic. Google form D, you have 10 seconds. A, B, C, D, sine, linear, quadratic, exponential. Fill in the dot, dot, dot. Hint. This isn't a guess. I told you the answer to this at the beginning. The correct answer is linear. We are looking for a linear restoring net force. For instance, if I've got something on the end of a spring, the spring is a linear function, directly proportional to the position, right? If the position gets longer, the direction of the force is in the restoring, shortening direction. If the spring gets shorter than its equilibrium position, the direction of the force is in the restoring, lengthening direction. Yes, that is a linear restoring net force. If you add a constant gravity term, if I do have a vertical, total force would be a weight and spring force. Gravity being a not linear, but a constant force. Constant does not change the fact that you still have a linear spring. So I'll just throw this out there. Vertical oscillations, horizontal oscillations, no difference whatsoever in the oscillatory properties of the system. You need a linear total force. Okay, now here we go. Here is everything I've been doing has been leading up to this point. Here's the central equation for spring vibrations. Everything else has been building to this. The frequency of simple harmonic motion never, ever, ever depends on its amplitude. The frequency of simple harmonic motion depends on the properties of the system. Ooh, that's a theme that I've been playing all semester. The properties of resistances. Sorry, the resistance of a resistor does not depend on the electrical signal through it. It depends on the properties of the resistor. The capacitance of a capacitor does not depend on charge and voltage. It depends on the properties of the capacitor. Well, the oscillation frequency depends only on the oscillator itself, the mass and stiffness of the spring. Bam, there you go. Note this is omega, not F. If you want the cycles per second, if you want the period, you have to convert using those formulas I gave before, okay? But still, how wiggly is the oscillator? How rapidly does it oscillate back and forth? That depends only on M and K. It does not depend on how big the wiggles are. I will demonstrate this. I don't have a spring. I will demonstrate this with my other system. Here, I'm going to make a dumb pendulum here. I'm going to make a very dumb pendulum. The corresponding terms, as I'll tell you officially on Wednesday, for a pendulum is just the length of the string. So I'm going to change the length of the string, and we're going to observe 4 different parameters: a big oscillation, a small oscillation, a big oscillation, a small oscillation. Count for me, count for me. Measure the period with your eyeballs. Okay, we're going to get a feeling for the big oscillation and the small oscillation. 1, 2, 3, okay, right? That's a big oscillation, slow period. Now let's make a big oscillation with a short string. Do you think it'll be the same or different? 1, 2, 3, 4. Yeah, very different, right? So a shorter string, both had big angle oscillations. They had very different periods, different angular frequencies, different simple frequencies. Now let's try, I think this is my original. 1, 2. Instead of having a big angular swing, let's just have a very slow angular swing, okay? And I'm just gonna, here's the equilibrium, I'm gonna displace it just a smidge. Watch carefully. 1, 2, 3, you see? Doesn't matter whether it's a large angle swing or a small angle swing. This was slow and small. This was big and fast. The time was the same. Let's try for a short oscillator length, okay? Here's the big oscillation. 1, 2, 3, 4, yeah? Now I'm gonna barely displace this. Look carefully, might be hard to see. 1, 2, 3, 4. Do you see? You could try this yourself. Dangle your roommate from a rope or something at the dorm window and count their period. You'll see that the further down they are, the bigger their swings. No, don't actually do that. You can imagine doing it. The further down they're dangling, the longer it will take. Go to the playground. Don't dangle the kids, please, but take a note. Big kid versus little kid. Big kid versus little kid on a pendulum on the swings. You yourself can get into those swings, and you will notice that the period of oscillations, if you're not pumping your legs, if you are not disturbing the system with external energies, the period of oscillations is fixed by the length of the swing sets chain, right? So if you are swinging back and forth, if you're swinging back in a very gentle swing versus a big swing, it takes the same amount of time for one oscillation. It is not the oscillation that controls the frequency. It is not the oscillation that controls the period. What controls the frequency of oscillation on a swing set is wrap that chain around a couple of times so you've got a swing set very close to a short effective chain. Try it. Try this. Everyone go to the swing set tonight and try it. You'll find that the shorter the chain, the faster the period of the oscillation. Okay, have you done this? You remember being 7 years old and doing this? Yeah. I know, it was a long time ago for me too. They're actually even longer, you'll never believe this, longer ago for me than it was for you. Okay, now it is time to make a kinematics connection, which is to say it is time to dust off ancient memories, ancient traumatic memories of position, velocity, and acceleration. What is velocity in terms of position? It is the slope of position. What is acceleration in terms of velocity? The slope of velocity. How do we see accelerations on position graphs? Curvature. We didn't do this much, if at all, last semester, because I didn't give you changing accelerations. Also because you don't know how to calculate, unless you know calculus, you don't know how to calculate curvature quantitatively. We're just going to do this qualitatively, though. We're just going to be able to identify, is there or is there not a curvature, in which direction it is. Foundations for what comes on the next slide. Velocity is the slope, the rate of change of position. Acceleration is the slope of velocity, which means that if we're looking just on a position time graph, we see velocity by slope. We see acceleration as curvature. Here's how to identify curvature. Let's talk about curvature for half a second. You need to be able to see this. Straight line, that's not curved. That's not a curve. It's straight line. Straight lines have zero curvature. In other words, if your position graph is a straight line, there's no acceleration. Actually, that should kind of make complete and total sense, right? Straight line has a constant v, constant slope. If v is constant, there's no acceleration. Well, duh, right? Where we see curvature is if slope is changing to be less negative, more positive. That's positive acceleration. We are decreasing my negative. We are increasing my positive. That is positive acceleration. Or if I have a positive acceleration which is tapering off or increasing negative acceleration, that's a negative curvature. Think about it. If I'm moving in the positive direction, slowing down, stopping, turning around, speeding up in the negative direction, isn't that a negative acceleration? The stupid way to get this fast is if you have a cup shape. If the cup holds water, it's positive. If the cup is a sad face, he's negative. Yeah, you see? You see? Here's my happy cup. Here's my sad cup. Positive versus negative. Let's apply that now and reason about an oscillation. Here I have graphed a mass on a spring which is starting at the equilibrium position and moving upward, then moving downward, then moving upward again, and so on. What is happening velocity-wise when position is going through equilibrium? Am I moving when position passes through equilibrium? Yes. Look, is there a slope to the position graph? Yes. What about when I am going the other direction through the equilibrium? Is this line sloped? Oh, you betcha. Is the line sloped when I pass through equilibrium position? Yes. Whenever you pass through equilibrium, in fact, you are at maximum speed. You can write that down. Take that to the bank. That is an always true statement. For an oscillation, your speed is maximum when your position is at equilibrium. I mean, stupid example of a pendulum again because I didn't bring my right in the kneecap. Okay, stupid example. When the pendulum is passing through vertical, is it moving? Yes. That is, in fact, the fastest instant of motion. When the pendulum bob is at its lowest position along the swing, that is when it's got the most kinetic energy. It's moving the fastest. So you have biggest speed, whether positive or negative direction, positive velocity, negative velocity, positive velocity, negative velocity. You have your biggest speed when you are crossing equilibrium in position. When do you have zero speed? You have zero speed at the instance that you are turning around, either at the peak or at the trough of motion. For instance, right there, at that instant you reach your highest point. Think about it. What was your velocity? Your velocity was positive. Your velocity is about to go negative. What is halfway between positive and negative? Was positive about to be negative? That is zero velocity. At the instant you turn around, you are not moving. Just like at the instant you reach your highest point of a thrown object, you are not moving. At that instant, your velocity is zero, and your acceleration is maximum. Maximum negative in this case. You are in negative cupped position. That means at this instant, at this peak height, you are accelerating downward. Well, think about it. That should actually make some kind of sense. If we are moving in the positive direction, about to be moving in the negative direction, we are changing from pluses to minuses. That is a negative acceleration. Think about it from a force perspective. If I am a mass on a spring and I have reached the longest length of the spring, which direction is the spring pulling me back? Spring is exerting a big force to pull me back from being long. The spring is exerting a compressive force, a force in the opposite direction. Force pulling me in the opposite direction of my displacement. Look at the trough. Here I have reached maximum compression. My spring is as short as can be. When the position is minimum, which direction is the net force? It is to re-expand the spring. The concavity is the opposite sign of the displacement. Displacement is negative, concavity is positive. Concavity is positive. Acceleration is positive when position is most negative. What's the slope here? Maximum. Maximum positive or negative? Negative. What's the concavity here? Is this curved? No. So, moral of the story, let's talk about positions, let's talk about velocities, let's talk about accelerations. If position is a sine wave, we start out with Big positive velocity, go through zero velocity. Big negative velocity, hit zero velocity. What kind of graph starts with a big positive, goes to zero, goes to big negative, goes to zero? This is sine. Sine starts at zero, goes 0 plus 0 minus 0. Cosine starts from plus 0 minus 0. The velocity of a sine wave is a cosine wave. Write that down. If your position is a sine, then your velocity is cosine. And look. What's acceleration? When position is zero, is acceleration positive, negative, or zero? Acceleration. No, not at all. There's no curvature here. There's no curvature when x is zero, acceleration is zero. When x is negative, acceleration is positive. When x is positive, acceleration is negative. When x is zero, acceleration is zero. Can you track through that? So if position is a sine, velocity is a cosine, and acceleration is a negative sign. Negative sign starts at zero, has zeros where positive sign has zeros, and has negatives where sign has positives, and positives where sign has negatives, okay? If you've taken calc, derivative of sine is cos, derivative of cos is negative sine. I've spent 10 minutes just saying calc at you without saying calc. If you've taken calc, Merry Christmas, you already had that knowledge. There's a connection. But you don't need calculus. You can look at the graph and logic through it. Here we go. A mass is undergoing simple harmonic motion. When its displacement is zero, it is at its equilibrium. That's how I define equilibrium. Tell me, at that moment, tell me about its speed and tell me about its acceleration. A, B, C, D. As soon as I can log in, your time's up. If I can log in. Oh, for dog's sake. I'm a pedant, I have to type a password. Peasant, not pedant. I'm always pedantic. Yay, correct. Correct answer is A. You get max speed and zero acceleration when you were passing through zero. One more way you can know that this is true is if you look at the equation, F equals ma equals negative kx. When x is zero, what is A? Zero. When x is big positive, what is A? A negative times a positive is a big negative. When x is negative, negative is positive. Acceleration is negative when position is positive, positive when position is negative, and zero when position is zero. Just go back to this F equals ma equation, yes? Do you guys remember F equals ma? Good. Okay, I would hope. That's qualitatively, here's the shape of the graph, here's what's happening when that's happening. You can't do this without calculus, so I'm just going to Merry Christmas give you the peak amplitude. I want to emphasize something. Thou shalt not divide distance by period. Thou shalt not divide distance by period. Thou shalt get the wrong answer if thou dividest displacement by period and calls that a day. That is, distance divided by time gives you the average speed, and sinusoidal motion is not smooth motion. Do not divide amplitude by time and think you've got velocity. You'll get it wrong. How do you find the actual peak velocity? I told you that if you've got a sine wave, you could find a cosine wave velocity. If you've got a cosine wave velocity, you've got a negative sine wave acceleration. But how tall are they? Very simple formula, a omega and a omega squared. And what we were reasoning through before, sine wave goes to cosine wave goes to negative sine wave. Set that aside for a second. That's the directions. Let's just talk about amounts. This a omega and a omega squared are the maximum, the amplitude of the sine wave, the amplitude of the velocity wave, the amplitude of the acceleration wave. Please note, acceleration and velocity are also sinusoidal functions, right? The height of the velocity sine wave does not have units meters. The height of the velocity sine wave is a speed versus time graph. That still has an a omega meters per second amplitude to it. When I talk about amplitude in general, I'm talking about meters. Perhaps most generally, I'm going to talk about meters. If I'm talking about velocities, this is the peak, the maximum intensity of that sinusoidal velocity wave. Okay, let's apply this. Got this? Yes? Yes, for realsies? Apply it and we'll be done. Apply it, we'll do a couple of review problems, then we'll be done. Google question F. Google question F and G. F, find me the freaking maximum speed. G, find me the maximum acceleration. If you get really big and really small numbers, you didn't necessarily do it wrong. Hint. Joules per Coulomb. What? Oh, it's from last week, Piper. I'm so, yeah. Please also note you must use omega, not F. I give you F, you need to use omega. Okay, answers up on the board. 2.2 centimeters a second and 19 freaking G's. Whoa, baby. 190 meters per second squared. Ready for a couple of review questions and then get out of here? Yeah. And the earthquake question. Okay. Earthquake question. Thank you. Real fast. Chop, chop. H. What the H? No, it's not. What's the default? Meters, kilograms, seconds, newtons, joules. Default. Good for seeing that, by the way. Okay, la respuesta correcta is, the correct answer is first, do not divide by 54. First, thou shalt convert and get period equals 3,240 seconds. Frequency is cycles per second. When I say frequency, cycles per second. So the reciprocal of 3,240 is about 3.1 times 10 to the minus 4 hertz. Bang. Questions? Doesn't seem that bad now that you've seen some other stuff, yeah? Okay, real fast. Let's go through some Google review, not some Google review. Let's go through some beginning of semester review. I, J, K, L, M. What is 20 parallel plus 30? I got a 20 ohm and a 30 ohm resistor. Add them in parallel. What's their total? Define voltage. Give the always true equation. The always true one, not the particular case, but the always true statement about voltage. What is voltage always equal to? Ditto for current. Don't need a question mark there. That's a statement. Thou shalt define voltage. Thou shalt define current. What's another one? What is true about ammeters? What is the internal resistance of an ammeter? Parallel plus. If you add a 20 ohm and a 30 ohm resistor in parallel, what's the total? Per person. 20 per person, 30. No. else did we do at the very beginning of the semester? Half a second, half a second, half a second. Sure. What current flows when a 3-volt, when 3 volts are applied to four ohms? Anyone who shows me 7 amps will be executed. Gesundheit. Oh, so many correct answers. Well, some correct answers. Oh, well, a correct answer. Just kidding. You guys are doing fine. No, words, no, 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 no. Tell me a number. Question I is, I have a 20 ohm resistor in parallel with a 30 ohm resistor. What is the total resistance? Is the equivalent of 20 plus 30. Parallel plus. I can absolutely review. Positively. Okay, so the correct answers are 12 energy per charge, charge per time. V equals IR permutations will get minus several thousand points for J and K. Watch out, if you're still writing V equals IR for these, after I believe 10 times, go out and get a tattoo, please. Preferably somewhere you look at every day. Internal resistance of an ammeter is 0 and current flows 3 volts, 4 ohms, 3/4 of a amp. Okay. If you want to stick around for questions as to why, I will stick around for a few minutes to answer, but let's let everyone go as this is the end of the period. But I had several whys and I will answer those. No. It is now only about 5% of the class that's saying V equals IR still. 95%. Now some people are still mixing up current and voltage. Still. In force versus position space, and that will result in oscillating amplitude versus time space. Ah, yes. Force versus position, bang, results in position versus time, bang. Those end up being mathematically provable, one from the other. Oh my God, everyone got 3/4, almost. Everyone got 3/4. Good. Okay, so V equals IR has been beaten in. And most people got the 0 ohms. Huh. No. Young's modulus is like resistivity. It is what hides inside. It is the materials constant that hides inside Spring's constant. Young's modulus is defined as stress per strain. Stress is pressure, strain is change in proportional change in length.
So strain is a change in length.
Yeah. Well, here. This is on MCAT, by the way. For MCAT study nerds and people. Here's what you need to know for MCAT. Young's modulus Y defined by stress over strain. And stress is nothing but force per area. And strain is nothing but, I'm going to write that as change in length per length. Yeah, something extends by 200%, its strain is 2.
Okay.
If something gets twice as, wait, hold on, I said that wrong. If something changes, if something's length doubles, then the change in length would be 1. That is the percentage change, not the ratio of final to initial.
So say we have a rope that's a meter long. That would be our bottom.
Yes.
And then we pull on 2 meters.
100% change.
And
Doubling 100% change.
oh, but it's only a change in 1 meter. So it'd be 1. Okay.
100% difference. 0% difference is if the length does not change.
Yeah.
Okay, so rearrange this. Y, well, let's clear the fraction, clear the big fraction. Joe. Well, let's get F. Let's get F alone. I like F. And I'm going to rearrange that in this way. Wait, hold on a second. Force, constant, delta L. Oh my sweet baby Jesus. F equals kx. This is the essence of the spring constant K. Just like capacitance, resistance, and everything else, it is a property of the material and the geometry. Y is the material constant. A and L are the geometry constants. The geometry, I wouldn't say constants, geometry factor. So just like resistivity, just like dielectric constant, whatever, Y, Young's modulus is something you look up. It is tabulated. It is a constant of the material. Then you want to build this into a particular piece of bone or whatever, healthy bone, diseased bone. I need the size, cross-section, and length.
Next question.
Sure.
Omega equals the square root of K over M.
I do. Mass out the end of the spring. K is the stiffness of the spring. No, you're going to have a massless spring and a springless mass. If you have a distributed mass spring, those equations get, oh, I'm not sure I could solve that actually. That would be interesting. Interesting to a professor means scary, by the way. Interesting with air quotes around.